All right, so I want to thank you for being here today on this great Thursday afternoon right before spring break. For some of you, it's this talk that stands between you and spring break. For some of you, you got class tonight. But regardless, thank you for your time and hopefully your patience as we get through this presentation, because I am Professor Matthew Simmons. I teach mathematics here full-time at the Nassau Center. And so whenever I was given the opportunity to do the last lecture series, which I knew it was going to happen eventually, when my colleague, Professor Shepard, did it several years ago before COVID, I said, my time's going to be coming. And what's the math guy going to talk about? Because people don't really like math. But and it just so happened that this is the year that I got the nomination, and I said, guess we're going to do it. So my presentation is Modern Math, Historical Roots, Future Findings. And yes, it is going to be math-based. But yes, it's going to be fun math-based. So a little bit of history and background about me. I am born and raised in Nassau County. I'm an alumni of West Nassau High School in Callahan, Florida, back from 2009. I am actually an alumni of FSCJ as well, earning my AA degree in 2011, where I then transferred to UNF, earning both my bachelor's degree and master's degrees in 2013 and 2015, respectively. And then just recently, I started in 2018, but just recently, this past December, I earned my doctorate degree in higher education administration, and so now I don't have to do school anymore. Well, except for the fact that I teach it, right? So, I mean, I guess, you know, I'm sentenced to school for the rest of my life, but I've always loved being a student, always loved being a learner. Like, I have a passion for teaching, I have a passion for learning. But during all of my degree programs, like I was doing the count. I don't know if I missed anything. So I said approximately 30 math courses is what I took all during my college years. And some of the coolest courses I took that weren't necessarily like mathematically difficult, but mathematically cool, were history of math and modern geometry. And those two courses specifically gave me myself like kind of a new perspective on math and a new appreciation of math and kind of a renewed interest in math. So I'm very grateful, you know, that I got the chance to take those courses, because they were elective courses, meaning you could choose from a pool of different options. So I think I got lucky and picked the coolest too. So real quick though, the purpose of the last lecture series is basically saying if I was to totally disappear off the face of the earth, and this was my last lecture, literally, you know, what message would I want to leave you with? And I started thinking about this a little bit, and I was kind of conflicted on the message I would want to leave you with. And I started thinking about every time I talk to someone and say I teach math, Matthew the math professor, I always hear the following comments. They're like, hey, I was never good at math. I'm like, yeah, okay. When am I ever going to use math? And then math was always my worst subject. Or I hate word problems. Like, I hear these things all the time, and I'm like, well, nice to meet you too. Let's do a handshake. So what my point here is, or what's going to be happening here is, you know, I hear a lot of stuff. People are scared of math, afraid of math. They don't think they can do math. But the issue is they actually can, and they do it more often than they think. Brief intermission for the truth. What is the truth? We don't know the truth, but what I think is the truth is, first, there is math all around us. The second one. It'll be coming shortly. Maybe. We actually math more than we think, whether you realize you're doing it or not. The third one. The suspense is killing us here. Dun, 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 dun. Math is innate to human thinking, meaning like we're born literally doing math and being a part of math, and we don't even realize it. Yet we talk so much trash about math, it seems. Yikes. And my favorite thing actually is the following. Math is fun. A little bit of history about that picture. One of my older brothers actually had a t-shirt he wore, and he was a math teacher, high school level. My whole family basically teaches, and most of it's math and science, but he would wear his Bert and Ernie shirt that said math is fun. And I think it kind of really is. So notice though, the only thing Bert and Ernie are doing is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's like there's a lot more to math than that. So that actually brings me to the next point here after we talk about a quick overview. The roots of counting is where we're going to start, because that's kind of where it all began. Then we'll move into talking a little bit about ancient Egypt and some of the stuff they did mathematically without actually realizing it. We'll talk a little bit about pi, because after all, it is Pi Day, March 14th. And then I want to talk a little bit briefly about the Babylonians and some of their contributions and what they did mathematically that they didn't really realize, was math. And then we'll talk briefly about Pythagorean theorem and why Professor Shep likes to walk on the grass all the time. And then we'll talk about math in the future. So to begin with the roots of counting, first off, mathematics actually wasn't a word until closer to approximately 600 to 300 BC. It was first used by the Pythagoreans to describe the study of anything or learning about anything. Very broad term. It's from the Greek word mathemata. However, even though mathematics wasn't coined yet, and it wasn't a phrase that was used yet, we had our Egyptians and Babylonians that were still dealing with issues of a quantitative or a spatial nature. And that was thousands of years ago. That was way before 600 to 300 BC, way before that. And basically, we have evidence that counting and recording existed nearly 30,000 years ago. That's a long time ago. And I'll show you the evidence on the next slide. But counting and recording, we needed it for like counting livestock way back in the day. They needed it for tallying objects when they were bartering, for counting days in a year, some way of keeping track of things. So for instance, like I always joke with my classes on the first day, I'm like, you're my class, you're my biggest class, you got 27 people in here. I have a jar in my office with 27 pebbles to represent your class. Because that's actually what they used to do. Like when farmers would let their livestock go out for the day or their sheep, when they would come back in, they would say, okay, 20 sheep went out. They didn't say the number 20, but they had 20 pebbles to represent 20 sheep. When they came back in, they'd say, okay, this sheep came back in, remove a pebble, another sheep, remove a pebble, until they had no pebbles remaining. So the sheep all were back if all the pebbles were gone. So that's some of the things that they did in terms of counting. And kind of what's really cool is there is actually an artifact that does exist. Too far. So there was a shin bone from a young wolf that's dated to be about 30,000 BC that was found in Czechoslovakia, and that was in 1937, so kind of 1900s there. And there were 55 notches on that bone that were grouped in fives. And so below is an example of those notches found on the bone. If you do look up a little bit close, you see kind of like little tally marks and stuff. Specifically, the bone that was found did have groups of 5, which is how we do tally marks to this day. So there is actually evidence of the concept of numbers and counting that does exist. So let's move specifically into talking about ancient Egypt. So most of what we know from ancient Egypt, dating back to around 3500 BC, is found from stone tablets, things that were engraved in stone tablets, and then records on a type of paper called papyrus. The ancient Egyptians, they actually used symbols to initially do their counting. For instance, if you had a little vertical staff, that represented 1. If you had like a lotus flower, that was 1,000. And if you had, this is always a favorite among students, the astonished man, he was worth a million. So astonished man was actually worth 1 million. The astonished man. Go back. It's going backwards now. We're going back in time, literally, guys. Let's go back forwards. Anyway, so they had this numbering system, but notice that we had like a symbol for 1, a symbol for 10, a symbol for 100, a symbol for 1,000, a symbol for 10,000. Everything was in terms of tens. It was a base 10 number system, just like ours. We have ones place, tens place, hundreds place, thousands place. So as a quick example, how they represented numbers, the ancient Egyptians, is they would provide a series of symbols. So like we have 2 lotus flowers, so that's 1,000, that's 2,000. We had 5 coiled ropes. Ooh, we can zoom in too. We don't want to do that. There you go. So we have 5 coiled ropes, so that was 500. We had 6 heel bones, so 60. And then we had 3 vertical staffs, so that was 3. So this number came out to be, so you can see it visually, 2,563, 2,563, 2,563. That's how that number was represented. So that's an example of how that was used. Next, something interesting they did in terms of multiplication. So in their items we found, whether it was papyrus or a stone tablet, we would see word problems written down. And one such word problem said there's a rectangular room that has dimensions 19 cubits by 50 cubits. It says, what is the area of the room? And we're thinking, well, what is a cubit? It's a cubit's the length from the elbow to the tip of the middle finger, typically about 18 inches. So how they did this, to find area, we multiply 19 times 50. They use something called the doubling method. So what they do is you list 1, double it to get 2, double it to get 4, double it to get 8, double it to get 16. That's the first column. In the second column, we take the bigger number that will be in our multiplication problem, and we write 50, double it, double it, double it, double it. And how they did the multiplication is they did the following. On the left-hand column, they selected the necessary numbers needed to add up to the 19. So that would be, in this case, 1, 2, and 16. Yeah.
If there's a delay, I think you can hit the right side of the screen too, just if
the right side of the screen?
You should be able to hit the screen.
And I think it'll advance the slide just if your clickers, if there's a delay on it.
That'll be good if so. We'll try it. We'll see what happens. So then we have 1, 2, and 16 add up to the 19, the smaller number. Then we take the corresponding numbers from the second column. There we go. I like that. I'm going to get a job on Wheel of Fortune. We choose the 50, the 100, and the 800. The corresponding number from the right-hand column, 50, 100, 800, adds up to 950. That's how they did multiplications, one of the algorithms. It's called the doubling method. A little bit different than our approach today. A little bit different than probably the approach they'll have hundreds of years from now too, or thousands of years. Who knows? So that's kind of some of the cool things that our ancient Egyptians had. So evidence of math in ancient Egypt, some other stuff here. So for agriculture, they actually had to use geometry to measure and divide land. They actually used ropes with knots in it. And the reason why this was so necessary is because annually the Nile River would flood, and it would actually affect, based on how far the river went back down, it would affect everybody's land that they owned. And of course, back then they actually did have taxes, unfortunately. So, I mean, you pay taxes on your land, so they wanted to make sure what land you had was marked correctly. Second, those pyramids that the Egyptians built. It'd be so cool to see one in person, but we unfortunately couldn't bring one here today. But the construction required the use of slope, volume, Pythagorean theorem. And then there was a papyrus called the Moscow mathematical papyrus. It actually included information about solving quadratic equations and some various volume formulas. And this is the Egyptians. There was no such thing as math. Not the word anyway, but they were doing it. And then there's the Ren papyrus, which dates to around 1650 BC, and it shows processes for solving linear equations, and there was actually an approximation for pi. Which brings us to our next slide, talking about pi. So as I told you, in some of these documents or items that we found, these historical artifacts, there were word problems in them. They literally wrote down word problems. And in the Wren Papyrus, problem number 50, it said to find the area of a round field with a diameter of 9 ket. So here we have a circle. It has a diameter of 9 ket here. And in this Wren Papyrus, where it shows the solution, it says, this is based on their knowledge, their experience, what they believe to be true. They said if you take away 1/9 of the diameter, so take away 1 ket horizontally and 1 ket vertically, just like that. This is a square now, 8 by 8. The area is 64. And if you plug this or use this information, use the diameter of 9 and use our area of 64, and you look at our area formula today and leave pi unknown, the pi approximation that the Egyptians came up with, and this was, thousands of years ago, the approximation they had was actually 3.1, which is right on point to 1 decimal place to what we know pi to be today, 3.1605. And that's the Egyptians. No such thing as math, no formal necessary training or anything like that. So that's honestly pretty impressive. And to this day, actually, with pi, it's irrational. It goes on forever and ever and ever. Like, we're never going to know all the decimal places of pi. It's kind of a dark truth, but we know several decimal places, but we never know the end of pi. It's irrational. There is no ending. So that's our little contribution to pi on Pi Day. Make sure you get some circular chocolate chip cookies if you didn't get any after we're done. So this will bring us over to our next society here, the Babylonians. So the Babylonians and Egyptians, they weren't like intermingling with each other. They had their own silos, so to speak. Like, we didn't have telephones back then, so a little hard to communicate. The way they counted was a little bit different. They just had 2 symbols. They had a peg, which represented 1. They had a disc, which represented 10. And their number system was actually a base 60. And how number systems work is base 10 means your first place value is 10 to the 0. That's 1, 1's place. Your second place value is 10 to the 1st. That's 10. That's why we call it the tens place. Your third place value is 10 squared. That's 100. That's why it's called the hundreds place. Then you have 10 cubed, which is 1,000. That's why we have the thousands place. Theirs was base 60 though, so they had 60 to the 0, 60 to the 1st, 60 squared. Those were their place values, which is totally out of whack and bizarre compared to what we're used to, personally. All right, so basically every group of 1s and 10s, every group of disc and pegs represented a place value. For instance, in this specific example that is shown here, my first group of disc and pegs represents the 60 to the 1st power place value. That's 43. There's 43 times 60 to the 1st power. And then that second represents the 60 to the 0 place value. There's 10, 20, 25 there. So to calculate the value of this in our number system, we take the 53 times 60 to the 1st plus the 25 times 60 to the 0. So we perform that calculation to end up getting that number there represents 3,205. So that was their way of representing it. It's a base 60 number system. So we're thinking multiples of 60. Multiples of 60 are actually used a lot in today's society, believe it or not. That base 60 system, think time, 60 seconds in a minute, 60 minutes in an hour. Think 360 degrees in a circle. So the base 60 concept is actually a little bit more popular than we probably think it to be. Even though our number system's base 10, that concept of 60 does exist around us. And they actually had processes for solving quadratic equations as well. This isn't math class, so that's why there's no quadratic equations in here. They had lunar calendars to help predict eclipses, so that was kind of cool. And if there's one thing that's the coolest out of all this, it's the name of the Plimpton 322 tablet. That's a pretty cool name in my opinion. It dates to around 1800 BC. And it actually lists some Pythagorean triples, numbers that create a true statement when plugged into the Pythagorean theorem. The Pythagorean theorem, as a little reminder, applies to a triangle that has a right angle. It says if you square each leg of the triangle, add the results together, it will equal the hypotenuse squared. So like 3 squared plus 4 squared is 5 squared. There was also another tablet dated around 1770 which talked about using Pythagorean theorem to find diagonal of a rectangle. As you can see, the rectangle appeared behind here. The hypotenuse, or the diagonal of the right triangle, actually is used to find the diagonal of a rectangle. So Pythagorean theorem could be used to find the diagonal of the rectangle. They did that. And so, this is not necessarily dated back to Babylonians and Egyptians, but it's kind of a friendly proof that doesn't take a whole lot of mathematical knowledge to be able to prove the Pythagorean theorem or actually derive it or know where it comes from. So all I have here is a square with another square inside of it slanted diagonally, literally 2 squares. The inner square has dimensions c and c. Could be 8 and 8, whatever. The outer square is a plus b. The side is measured a plus b. A and b create a plus b. Don't open that. So area. If I wanted to calculate the area of this entire object here using the dimensions of the outer square only, we said that the outer square is a plus b. So if you take a plus b and multiply it with itself, you square it, you'll get a squared plus ab plus b squared when you FOIL out the 2 binomials or know the squaring shortcut. Regardless, you get this a squared plus 2ab plus b squared. That's what you get. That's whenever I use the outer component of the square, the outer side dimensions. When I use the inner square in the triangles, so I'll use the 4 triangles and I'll use that inner square. The area of the 4 triangles, we know the area of a triangle is 1/2 base times height. And there's 4 triangles total. 4 times 1/2 is 2. Your triangle dimensions are a and b, so you have 2ab. If you look at the inner square, so we got the 4 triangles done, and the inner square is the side of measure c. C times c is c squared. So your total area of that approach is 2ab plus c squared. So I just calculated area of the same object 2 different ways, and I got 2 different results. But they're equal to each other. They're equal to each other. Both have 2ab. We can cancel it out, and look what we have. A squared plus b squared equals c squared. And that's literally us using a picture to derive the Pythagorean theorem, to come up with it on our own without listening to anybody else. And there's derivations, there's proofs everywhere for it. Like up to this day, for instance, one of my brother's professors at UNF, his daughter actually came up with the proof of the Pythagorean theorem in the past decade. So up to this day, like proofs are being developed, or things as simple as this. Like it doesn't have to be complicated. It's just area. So one practical use of Pythagorean theorem here is the out front of the building here in Nassau Center. You know, when I leave, I'm a good boy, and I walk out on the sidewalk and over on the sidewalk to get to the parking lot. There is a certain other faculty colleague here, I won't say his name, but when he leaves at the same time as me, he dashes right through the grass. And I'm like, what are you doing? Get off the grass. I almost got written up in middle school for being on the grass, in-school suspension for walking on the grass, so I'm a little bit picky about that. And of course, this colleague says, you know exactly what I'm doing. You know the diagonal is the shortest distance by the Pythagorean theorem, so you know, he wins that case, I guess. He wins on that note. But yeah, we use Pythagorean theorem. That's him using math without even like actually, I mean, he's the English guy. Oops, I kind of gave out who he is now. Sorry. Anyway, but I mean, that's just us using math without realizing it, like just naturally, hey, I'm just going to go to diagonal because it's the quickest way. It's not like he's doing a Pythagorean theorem calculation in his head, but he knows, like it's intuitive that that diagonal's the shortest distance. So that's kind of just real life what's going on there in terms of like just doing math without realizing it. So math for the future. The basis of math has been around since, well, the beginning. The need for counting, the need to understand our surroundings, etc. The way we math has changed. Obviously, we don't use like the Egyptians' doubling method nowadays. We have our own calculators or multiplication procedures that we use, but the overall purpose has remained the same. We still try to quantify and understand the world around us. And there's still much to learn, and perhaps we're blindly actually coming across mathematical relationships in our daily lives that we don't realize are going to be formally identified as great findings later on. Like civilizations 1,000 years from now might look at something we're doing that we don't realize is important and be like, hey, no, that's something important. Like that's something that's not really actually known or written down or a known fact or knowledge. So it makes you wonder, like as we go through our lives each day, even though you're not intentionally doing math, like what are you, you might be doing something great without knowing it, and how cool is that? So it's only natural that we interact in complete mathematical activities daily, even if it is just walking on the grass, whether we know we're doing it or not. So the big questions actually are, has someone really never been good at math? Like, I mean, there's a lot of different things contained in math. It's not just solving quadratic equations, which I didn't want to show any. Do we ever actually use this math? Yes, we walk on the grass. Is math really my worst subject? I don't know. And do we really hate word problems? Like our life is a word problem. Like we're a word problem, we're solving problems every single day. So maybe word problems aren't so bad. So that's basically where I'm going to leave off here. What's left for us to find? I don't know, the future is unknown, but it would be cool if we actually do discover things that are great. And perhaps our greatest discoveries are going to be found with us actually not knowing that we found them. And remember, most importantly, the one thing that I'll leave you with here is, you may say, I hate math, I don't like math, but you're thinking about math formally as a subject that you're being, you're in class trying to learn or what, but math is all around us, and there are, after all, so many different ways to math, even if it is just walking on the grass. So, and that concludes everything for today. So thank you for being here, and we're good. I can retire. All right.